Hi, my name is David, and I'm a student in the Visual Information Processing department. And the paper I'll be presenting today is called Auction-Based Optimal Task Offloading in Mobile Cloud Computing. Okay, so I'm going to be starting with the objective of the paper. Then I'll go into the research background. Then we'll go into the problem setup. Then we'll go into the algorithms, and we'll end with the results and discussion. So the objective of this paper, it's really starting with the trend of these days, there's a lot of resource intensive apps being used on smartphones. For example, voice recognition, face recognition, apps that are able to find songs based on audio samples that you submit. These are all apps that might be too heavy to run on locally on a mobile device. And so the cloud is used to process most of to do most of the processing. But there are some disadvantages with this method, which is that it causes longer latency. There's higher energy consumption, and the wireless signal can be intermittent. So this paper uses auction theory to optimally assign tasks to available devices. It basically finds a better way of assigning tasks to the right device rather than just assigning everything to the cloud. It uses a three-tier architecture whereby first it tries to find nearby mobile devices that it could use, and then it tries to find nearby cloudlets. And if all else fails, then it uses the cloud. And they call this method the selection of best destination to offload, or abbreviated as SOPTO. And so the goal is to minimize latency and energy consumption, and the evaluation method is by using simulations and trying it out on a testbed, like using testbed experimentation. So the ways of using the cloud are largely, there's 5 different ways. So the first way is the cloud that everyone knows is using a remote cloud, connecting over the internet and using that to do the processing. Mobile cloud computing is similar, but instead of using a remote server, it just uses nearby mobile devices, notebooks, tablets. Drop computing combines cloud and wireless in a 2-tier cloud. Cloudlets are a little bit more higher spec devices than typically used in mobile cloud computing. But there also is like finding mobile devices in the vicinity and providing the services ad hoc, so upon request over Wi-Fi. And then edge computing is basically trying to push as much of the computing to the local device as possible. That's a recent trend with like IoT and devices like NVIDIA Jetson. So this paper, their main contributions, they say, are threefold. The first is coming up with the system of SOPTO, which helps mobile devices offload tasks to suitable destinations. Second is you don't need any central, this method doesn't require any central intervention because it's a distributed method. And the third is that even though there's incomplete information, it can still make rational decisions by making use of auction theory. So the architecture is basically composed of 3 layers. First one is SOPTO 1. This is where it tries to assign an appropriate mobile device in the vicinity. This is based on the cost of offloading, and if it can't find a suitable device, it moves on to the next layer, which is SOPTO 2. And this is the same thing, but it tries to find an appropriate cloudlet. And if it can't find an appropriate cloudlet, then it moves on to SOPTO 3, which is moving the processing to a distant cloud. So to set up the problem, it starts by defining variables, and S is the source node. M represents the mobile nodes available within range. C are the cloudlets available within range. T denotes all the subtasks that the task has been divided into. And Y superscript M represents all the maximum number of tasks that can be offloaded to a given device. Y superscript C is the maximum number of tasks that can be offloaded to a given cloudlet device. And then this formula here just indicates that, well, Z is like a binary variable. It can only be 1 or 0. And it's 1 if that device J has been chosen to offload the task T, like the task TL2. So if it's been chosen, it's 1. And if it hasn't been chosen, it's 0. And you can only choose 1. Out of all the different devices, you can only choose 1 for each task. So that's why the sum of these, the sum has to sum to add up to 1. So now the UM and UC represent UM like the utility of all the devices for each task. So UM would be the utility of offloading given task to MI to a given mobile device. UC would be the utility of offloading a given task to a given cloudlet device. And utility is inversely proportional to the time to complete task and energy consumption. The objective of the source mobile device is to maximize total utility at each time step, which is given by these formulas. But to briefly summarize, R0 is basically the utility of executing at the source device. R1 is the total utility of executing in tier 1, which is the mobile devices, and R2 is the total utility of executing in tier 2, which is the cloud devices. And then the logic is simple. If R0 is the largest out of the three, then since it's the largest utility, then it will allocate the task to the source mobile node. If R1 is the largest, then it'll allocate it to the task to assign the task to a mobile node. And if R2 is the largest, then it'll assign it to a cloudlet. And if none of them, if it can't find a suitable one among R0, R1, R2, then it'll move it to the distant cloud as a last resort. So at time t, we're given a few additional variables. So Q represents the number of instructions for each task. So you can think of this as the size of each task. S0 is the processing speed of the source mobile node. VM is a vector that contains the processor speeds of each of the mobile devices. VC is also, it's the same vector, but contains the speeds of the cloudlets. And the delta K represents the minimum time to execute each task TK. And this is proportional to the size of the task, obviously. So the bigger the task, the longer it takes. And it's inversely proportional to the speed, obviously. So faster the processing speed, then the less time it'll take. And then the speed is offset by the computational load. So larger the load, the slower the speed. Okay, so the algorithm starts by, so algorithm is basically an auction. And then in the auction, each task is auctioned off by a source S, which acts as the seller. And then the mobile nodes M and the cloudlets C act as the bidders. And the maximum bidding increment is defined as the difference between the max utility and second largest utility. So P represents the set of pairs M and T where T is mapped to mobile node. So every time the T is mapped to M, it goes into this set P. And then out of the set P, if you take all the T's, all the tasks that go into this set P, that creates another set called AM. And then L is all the set of pairs where a task is assigned to a cloudlet. So where the cloudlets and tasks are matched, that goes into this L set. And then out of this L set, if you take all the tasks that belong to that set, that creates another set called BC. And then CT is the set of the mobile devices that are in P, and DT is the set of the cloudlets that belong to the set L. Okay, so the solution, the SOPTA 1 solution, this is for the first tier, the tier of the mobile devices. It starts with these two variables, which is IT is the remaining set of tasks that have yet to be offloaded, and IM is the remaining mobile nodes that are still available. So one of the mobile devices a given mobile device will calculate its time to complete each task, and it'll put that into a vector. So P represents all the times to complete each task. And it submits that to S as a bid. And so then the tasks are assigned to the mobile device by selecting the maximum utility. So for each task, the one that gives the highest utility is chosen as the mobile device with the highest utility is chosen as MIK. And then conversely, for each mobile device, the task that gives the highest utility is chosen as TKI. And the bidding increment is calculated as follows. It's basically the largest utility minus the second utility. You can find that here, which is like, this is the largest utility of the mobile device with the largest utility. And this is where the task is not equal to the largest utility task, the largest utility among the remaining ones, which means the second largest utility. So it's the largest minus the second largest. And it's the same here. Except here, it's like comparing the highest utility for the mobile device and then the second highest utility mobile device. And then you take all the bidding increments together, and the largest among those is denoted as G. And so the bidder M with the highest bid G is selected. And then if it is assigned then to a mobile device, then that task is dropped from IT, because this is a list of the remaining tasks. And so since it's been assigned, it gets dropped, and MI also gets dropped from the list of available devices. And if there's no suitable device here in tier 1, then it moves to tier 2, which is SUBDO 2. And that SUBDO 2, it basically does the same thing. So IT, remaining number of tasks, IC, remaining number available cloudlets. And then so it's the same process. The bidder submits its bids, which is the time to completion for each task. And then it gets matched based on whichever gives the highest utility. Cloudlet that gives the highest utility is C, CJK. Task that gives the highest utility for each device is TKJ. Bidding increments are calculated the same way. It's the highest utility minus the second highest utility. And then all the bidding increments are put together, and the highest among them, the maximum among them, is labeled as G prime. And the bidder with C with the highest bid should be G prime. G prime is selected, and then the task is dropped from IT, and the cloudlet is dropped from IC. And if there are any remaining tasks after all of this is done, SUBDO 1 and SUBDO 2 have all been completed, and there are still 2 remaining tasks that have to be assigned, then those are offloaded to a distant cloud. And so in the experimental setup, they specify n number of tasks, m number of mobile devices, c number of cloudlets. These are generated randomly from a uniform distribution between 1 and 100. Size of tasks and the device specs are also random. And then the effect of the task size is that SUBDO reduces completion time by offloading tasks. This basically, if you don't use SUBDO, then it's going to be, everything's going to get processed locally. So obviously that's going to take a long time. But since now, if you use SUBDO, it's going to offload some of those tasks to the cloud when appropriate. And so that reduces the completion time, as you can see from this chart. And then the bandwidth, they tried increasing the bandwidth of the cloudlets. And then what they observed was that as the bandwidth increases, the bandwidth of cloudlets increases, more tasks get offloaded to SUBDO 2, which is as to be expected, and you can see that from this graph. And as the computational power of cloudlets increase, more tasks are offloaded to SUBDO 2. So the more powerful the cloudlets are, they get assigned more of the tasks. Okay, and then they also did, besides this simulation experiments, they did some testbed experiments. So this is using actual devices. So the first tier was composed of 3 mobile devices, second tier 2 laptops, and third tier they used the Megalama cloud. And the task that they defined was to read, sort, and rewrite arrays of integers from size 5,000 to 100,000. And what they observed was that execution time increases with the task size. They found this surprising. Mobile tier was actually faster than the cloudlet tier, in spite of the cloudlet tier having higher spec. And the reason for that, they think is because the cloudlet tier had a higher CPU load, which slowed it down. And the effect of the bandwidth is that what they found was that the Wi-Fi Direct had a much higher performance than the Wi-Fi and 3G, and they excluded Bluetooth from the experiment because they found this performance was just not good enough. And but when the data size is small, what they observed is that the performance is actually similar between all the different methods. So effect of task type. So when they're trying to decide whether to process locally or offload to remotely, you also have to consider when you process it locally, it takes a certain amount of energy, but then offloading it also takes a certain amount of energy. So so they wanted to figure out when does the load of offloading or when does the load of sorting locally begin to become bigger than the load of offloading to a remote device. And they found that happens when the task size reaches 50,000 or goes beyond 50,000. From that point, it might make more sense to offload, since offloading will take less energy consumption. And that's what this is saying here. And that's the end of my presentation, and I hope you enjoyed it. Thank you for listening.